In this section, we're going to take a look at carbon-carbon bond forming strategy. And with the exception of organometallic type coupling, all of our carbon-carbon bond formations require us to have a nucleophile and an electrophile. So your nucleophile is either something that is negative or partially negative, and your electrophile is something that is positive or partially positive. So in the example below, this is our classic SN2 reaction. We have an organobromide, and we know that there's a dipole toward the bromine. So that means the bromine is partially negative. The carbon is partially positive. So that makes the carbon here an electrophile. And then in sodium cyanide, if we break that up into ions, we have sodium plus and Cn minus. And the negative charge on that Cn indicates that it's a nucleophile. So now we can do our carbon-carbon bond formation. Just draw a curved arrow from the nucleophile to the electrophile. And we break that bond. And we get the product. So here's your new bond, and what we've done is we've joined what was the electrophilic carbon and the nucleophilic carbon. So the thing to keep in mind is you can't join two electrophilic or two nucleophilic carbons. For example, down here, I have a carbonyl, which has a dipole. So that makes the oxygen delta minus, the carbon delta plus. So that carbon is electrophilic. And then the organobromide, just like we saw in the previous example, the bromine's delta minus, the carbon's delta plus. These two carbons here, because they're both electrophilic, they can't be joined. So if we want to somehow join those two carbons together, we somehow need to reverse the polarity of one of these two atoms to make it nucleophilic instead of electrophilic. So what we have here is a couple of ways that allow us to reverse the polarity of a carbon atom. And these are things we've seen before. This process of polarity reversal is often referred to as Umpelung, which I believe is like the German equivalent of polarity reversal. So the first way we can do this is by forming an organometallic reagent. So right now, this organobromide, the carbon here is electrophilic. If we add magnesium to this, the magnesium inserts itself between the carbon and the bromine. And now, because the magnesium is our more electropositive element, the carbon is now electronegative. So we have the magnesium, delta plus, the carbon, delta minus, and now this carbon is a nucleophile. Another way to reverse the polarity of a carbon is by forming a Wittig reagent. So again, same organobromide here. Right now, this carbon is electrophilic. If we turn that into a Wittig reagent by adding triphenylphosphine, which first gives us this, followed by butyl lithium, which will just deprotonate that carbon. Now we see the negative charge on the carbon, therefore it's nucleophilic. Now going back to the reaction we saw on the previous slide, we have our carbonyl, which is an electrophile. Then we can use either one of these nucleophiles to form the carbon-carbon bond. I'll just use the Grignard reagent. So now that we have that negatively charged or partially negative carbon, and we have a nucleophile, we can do the carbon-carbon bond formation. So the nucleophile attacks the electrophile. We'll draw the intermediate. Like that, and here's our new carbon-carbon bond we formed that was between the nucleophilic and electrophilic carbon. And then ultimately we generally protonate this to end up with an alcohol after a Grignard addition. So the whole point here is, in terms of synthesis, if you have two things that seemingly won't react, you can often do something to make one of those the opposite polarity so that you can react them together. So pause the video here and see if you can prepare this product using isopropanol as your only source of carbon atoms. Right? You can use multiple different molecules of this and do different things with each one, but this is your only carbon source. You can use any other reagent, so see if you can come up with a synthesis to get to here. And then when you're ready, you can play to see the solution. Okay, in synthesis, what you often want to try to do is find your starting material in the product. And since the product has 6 carbons, we know we're going to need 2 molecules of isopropanol. And we'll do different things with each one. And we can see one is pretty clearly still present. The other part of it is. So we lost the OH, but part of it's still in there. And we see that we are forming a new carbon-carbon bond. So to form that bond, effectively I need one of those isopropyl or isopropanol carbons to be an electrophile. So let's say I'll try to make this one the electrophile. I need the other one to be a nucleophile. Well, how can we do that? We can make this alcohol OH an electrophile in a couple of different ways. You could convert it to a bromide, but that would make it a leaving group and it would depart. But we want to keep the OH. So how can we keep the oxygen while making that electrophilic? Just do an oxidation. Now you have a carbonyl with an electrophilic carbon. But when you add something to this, only one of those bonds moves, so the oxygen stays in place. Now, how can we make the other OH into a nucleophile? Let's make it into a Grignard reagent, or an organolithium compound. So first we have to have an organohalide. So what I'll do first is use PBr3 to convert that to the organobromide. And right now, this carbon is still electrophilic, so those two wouldn't react. But then, let's just add lithium. We'll form the organolithium compound. Now, this carbon is nucleophilic. So we have our nucleophile, we have our electrophile. We can do the reaction. So when we mix these two together, the nucleophile attacks the electrophile. Here's our new bond. And now just add H3O plus, and that'll protonate the oxygen. And there's your product. I drew it a slightly bit differently here, but it's the exact same thing.